Okay, so I want to explain to you a little bit more what that slide means about um, specificity for identical protons. So basically, when we think about the catalyst having an active site, we have to think in three dimensions. And so, if we were to cut an enzyme, let's say we had an enzyme, so we have our enzyme. So we have our enzyme, and what we're going to do is we're going to take our axe here, our tiny, tiny little axe, and we're going to cut sections. We're going to chop this enzyme up into pieces. And so if we split it in half, so we're going to chop the enzyme in half, what we could see if we have the active site, let's say the active site is here. So here's our active site. So I drew it in little dotted lines because it's inside the enzyme, so you can't really see it from the outside, but it's there. So now what we're going to do is we're going to chop the enzyme down the middle, like an apple. And what we can find is if we look at the active site, one piece of the active site, so this is half one. So the active site's here. Then we can kind of shade it so that we can see that this is a curved, supposed to be curved away active site here. So, and then half two would be shaped something like this, so that there's some piece, some steric bit, right, that's changing the shape of the active site. And this is one of the ways that the enzyme imparts chirality onto its subject, or onto its substrate. Now, so if we look at the specific example, let's say that we have some molecule that's got, let's say, so we're going to make a specific example of what I'm calling diastereotopic substrate. And what that means is that it's a substrate that has two protons that are actually in chemically distinct environments. And if one of the protons was switched out, it would make a diastereomer. So in this case, we're going to have, this is our, we're going to have O, and then we're going to have R1. And then we're going to have NH3 plus. And then we're going to have some HA and some HB. So here's our substrate, right? It's got an O, and it's got an HA, and it's got HB. So now we're going to put that in the active site. So remember how the active site looks. We've got half one and half two. And what we'll also say is that here in half one, we're going to have, let's zoom in. Half one is going to have a negatively charged group, And then over here, it's going to have a serine. So this is maybe aspartate, and this is serine. And zoomed in, half 2, this piece right here is going to have a base. So this is going to be a base. And this base is a strong base. So this base is a strong base, and it's strong enough to deprotonate the substrate. Okay, so now we have our enzyme, and we're going to bring our substrate in. So I'm going to flip the substrate, remember, so that everything can line up. So we have our enzyme, we have our active site, and then I'm going to draw now the substrate in the active site. So we've got R prime over here. And now we've got HB, because I flipped it, is going to be coming out, and HA is going to be coming back. So I'm going to, oh darn it, I didn't flip it. I was smart. Ah! I outsmarted myself. Okay, let's draw that again. You don't even have to see it. Ah! Okay. Bring in our substrate. So we have over here from half 1, our minus, and our serine. And so over there, we're going to have our NH3, our NH3 plus, our O R prime. It's going to H bond. We're going to have HA and HB. Okay, so now you see what I did there? I have the enzyme, I have the substrate here. So I have the enzyme, I have the substrate, and now I drew in an ionic bond there on the left and an H bond on the right, and I have the substrate now in the enzyme active site. So now what I'm going to do, so I'll say substrate, is that if we bring in that same picture, but we bring in half B as the nucleophile now, So now I brought in half B. So I brought in that base from half B. And we're going to see that how everything's set up, B can only deprotonate HA with how that enzyme's active site is set up. So B can deprotonate HA, and then we're going to get to we're going to have a lone pair, HB in the center here. I'll redraw this. Redraw. You guys all fast forwarding through this. Should do some, take some deep cleansing breaths. Be over in just a second. So what we're going to have here, I want to make sure that I have drawn this in a suitably appropriate manner. You could say HB still going back. I think that's actually appropriate. Okay. So now we have this. It's a lone pair where that was. This is minus charged. Okay, that's beautiful. That is just beautiful. Okay, and we have our B from half 2. And the B is now BH, and I'm going to arbitrarily decide it was a plus. And so after the deprotonation state, this is what it looks like. So you see that now the B, that base has now got an H on it, and where HA was has been deprotonated, so there is that minus charge there. So the proton got removed and there's that minus charge there. And so this could react with some other electrophile. Let's say that the enzyme has now another electrophile that it brings in. From that same side. So let's say it brings in an electrophile. So I'm numbering that 2 because this happens second. And now if we have it as 3, that lone pair, the minus charge, is going to attack the electrophile. So we'll say anion. It's not a lone pair. Well, yeah, it is. I mean, so the anion attacks E+, and for the product that you're going to get is going to be So this would be the product that you're going to get. So that's a chiral center there. That carbon's attached to 4 different things. And so remember that how the binding of the enzyme is set up, that base is only going to be able to pull off HA. So that chirality is transferred from a prochiral, so a substrate that's not chiral but has the capacity to be chiral, from a prochiral substrate to a chiral product. So this is a very general view of how this works, but conceptually this is how this works.